Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska Fairbanks. Today I want to discuss the solution to problem 3 in the practice exam for the final exam. Starting with the multiple choice questions. In the 3-cell model, which of the following is true? And the first question is that there is a polar cell. The second one is that there's a polar cell, and the third one says there is a Hadley cell, and all of those cells do exist. But let's start with the first one, with falling air at the polar front and rising air at the pole. And this is wrong. The polar cell has rising air at the polar front, which is at about 60 degrees north, and falling air over the pole. If you will, it has rising air at its warm southern edge, if you think about the northern hemisphere, and falling air at its cool center. So that's where the polar cell goes wrong. The second answer is the right answer. There is a polar cell with rising air at the polar front and falling air at the pole. So rising at its warm southern edge and falling at its cold northern edge. In the northern hemisphere, this cell has southwesterly winds aloft. If there's rising air at the warm end, then the pressure gradient force is pushing that air from the warm column to the cold column, and so it's pushing it in the northerly direction, and then the Coriolis force is turning it to the right in the northern hemisphere, and so that becomes a wind heading northeast towards the pole and to the right. So it's a southwesterly wind aloft, and therefore when it falls at the pole it has to come back and fill the cell, because the cell is a closed loop circulation, and so it's a northeasterly wind at the surface. The dominant winds in the polar regions are northeasterly. So this is why choice 2 is right. And the last choice, there's a Hadley cell with rising air at the polar front and falling air at the pole, is wrong because the Hadley cell is at the equator. 2. Which of the following best describes an air mass? An air mass is a large body of air whose properties of temperature and humidity are fairly similar in any horizontal direction at any given altitude. And that's what we saw in the previous problem 2, when we talked about the fact that we can use humidity as an indicator of whether we're in an air mass that isn't changing, or we're experiencing a day where one air mass moves out and another air mass moves in. Choice 2, a boundary or transition between two large bodies of air of different humidity, is a front typically, and a large high pressure or low pressure system is a weather system. It can be a cyclone or an anticyclone. C. Which of the following correctly describes a cyclone in the northern hemisphere? A cyclone is 3, a center of low pressure. Because it's low pressure, air is rushing into the low pressure, and therefore it rises at the center. As the air spirals in, it is under the influence of the Coriolis force in the northern hemisphere, so it's moving to the right, and therefore looking down from above, if something's moving towards the center and moving to the right, it's moving counterclockwise. The choice 1 is wrong because of the clockwise direction. Choice 2 is wrong because a cyclone is low pressure, not high pressure, and choice 4 is wrong because a cyclone is low pressure and not high pressure. D. Which of the following real cyclones and anticyclones is predicted by the 3-cell circulation model? And what we're trying to highlight here is not just that you've memorized the circulation models, but points out that the 3-cell model, which is a very simple model, actually explains many of the features that exist in the actual atmosphere. And it explains the large low pressure systems along the equator, the high pressure systems in the subtropics, and some of the low pressure systems in the polar regions. The Aleutian low is not predicted because the Aleutian low goes away in the summer. The Icelandic low stays all year round, and it is predicted, but the Aleutian low does not. The Azores Bermuda high is predicted. It's at the subtropical anticyclone that sits in the Atlantic and greatly influences the weather of the American Southeast. And the Siberian high is a continental anticyclone that sits over Siberia in the winter when it gets very cold and you get sinking air under clear skies. the weather system reinforces itself because the clear skies and the descending air allow it to get colder and colder and colder at the ground, and so you set up this very strong high pressure system over eastern Siberia in the winter. That doesn't exist in the three-cell circulation. The three-cell circulation is about a planet that's a water planet primarily, and so you don't have the effects of low pressure systems forming in the summer and high pressure systems falling air forming in the winter. So in the three-cell circulation, for example, you can't explain the monsoon, which is due to a thermal low forming over Asia in the summer. The question E, which of the following best describes a thermal low? A thermal low is a rising column of air that forms over land as the land warms in summer. And again, one of those forms over the Mideast and Asia in the summer and is part of the monsoon circulation that forms in the summer. There's also such a thermal low forming over the southwestern United States that contributes to rainfall in the southwestern United States in late summer. I'm now going to turn the page for F to our circulation diagram and then talk about the correct answers in the framework of talking about the diagram. So the diagram shows a schematic picture of the Earth as the light blue circle. What I'm showing are red circles A1 through A7 that identify high and low pressure systems. The horizontal lines on the Earth represent the equator, 30 degrees north and south near B2 and B4, and then 60 degrees north and south close to B1 and B5. We have a three-cell circulation, and before I start, let me just talk about it. We have, due to intense sunshine, rising air at the equator, B3, upward rising air, and therefore at that latitude we have low pressure with the rising air. The air rises, and then because the equator is warmer than everywhere else, the pressure gradient force pushes that air out from the equator, and in the northern hemisphere it's deflected to the right, in the southern hemisphere it's deflected to the left, and it eventually begins to fall at about 30 degrees north. Let's just focus on the northern hemisphere for a moment. And so it falls at B2. So the first cell is a Hadley cell where air rises at B3, travels northward to B2, 30 degrees north, and falls, and then returns along the surface and rises again. And that's what we mean by a cell. And so this is a basic convection cell that we have in the Hadley cell. In the subtropics, from 30 degrees north to 60 degrees north, we have falling air at B2 and rising air at B1. We have, if you want, a thermally reversed cell because it's rising at the cold side and falling at the warm side. It's called the feral cell. And there's a high pressure at A3 at 30 degrees north where we have falling air, and there is low pressure at 60 degrees north where we have rising air in B1. And then finally we have a polar cell between 60 degrees north and the pole where we have rising air at the southern edge at 60 degrees north, and we have falling air at the pole, which is very cold, at the pole, which gives us a high pressure system at the pole. So the pattern of highs and lows matches the pattern of falling and rising air on each side of the cell. Where we have rising air, we have low pressure. Where we have falling air, we have high pressure. And so for part one of this problem, the answer is that if A1 is a high pressure system, then to complete the cell, A2 is a low pressure system. That completes the polar cell. The feral cell has A2 as low pressure, and therefore to complete the cell, it has to have A3 as high pressure on the other side of the cell. And from A3 to A4, if A3 is high pressure, A4 has to be low pressure to complete the Hadley cell. And as I continue into the southern hemisphere, A5 has to be high pressure, A6 has to be low pressure, and A7 has to be high pressure. The pattern is symmetric between the two hemispheres. And so the answer is A. The B and C answers, I've made all the high pressures in the one hemisphere and all low pressure in the other, and you cannot have such an asymmetry in the pattern. The pattern of sunshine, of sun falling on the earth at equinox, which is what the three-cell model shows you, is that there should be symmetry between what happens in the northern hemisphere and what happens in the southern hemisphere. They're mirror images of each other. through the equator. Then if I turn to the next question 2, where should I have rising and falling air as indicated by the bubbles B1 through B5? If B3 is rising air, the arrow going out, therefore B2 should be falling air with an arrow going back to the ground, and B1 should be rising air. B4 should be falling air, B5 should be rising air. So the pattern is that the rising and falling alternates as we travel in latitude, again completing the structure of each of the 3 cells, and so the answer is B. The 6 curves at the ground showing the surface winds. If I have rising air at the equator, then I have to supply that rising air from the ground, and therefore the curve C3 has to have the arrow tip on the equator side, the lower side of the curve. The curve C4 has to have the arrow tip at the top of the curve to supply the rising air at B3. If I go to B1, I have to have my arrow tips at C1 at the bottom of C1 because the air has to flow into B1 so it can rise. The C2 air is flowing into B1 so it can rise. If I go to the southern hemisphere and look at B5, air is flowing into B5 because it's rising air at B5, and so the arrow tips have to be at C5 at the bottom and C6 at the top. And so if I look at that pattern, if there's an arrow at the bottom of C1, it's a northeasterly wind. An arrow at the top of C2 is a southwesterly wind. An arrow at the bottom of C3 is a northeasterly wind. An arrow at the top of C4 makes it a southeasterly wind. An arrow at the bottom of C5 makes it a northwesterly wind, and an arrow at the top of C6 makes it a southeasterly wind coming from the southeast, and so the answer is A. In figure 3a, where are we likely to find jet streams? We're likely to find jet streams at the edge of the polar cell and the edge of the Hadley cell. Remember, a jet stream is formed when we have 2 air masses next to each other with a sharp change in temperature. If we have a sharp change in temperature, we have a sharp pressure gradient force across that boundary. And so, because we have temperature gradients at the junctions between the cells, we tend to get jet streams. We'll talk about this a little more later in the problem, but we do get jet streams at B1, B2, B4, and B5. At B3, we have air of similar temperature on each side of the equator, so we don't have a strong pressure gradient force across the equator. We do have pressure gradient force outward from the equator into each hemisphere. And finally, where do we expect stormy weather due to intense convection? Due to intense convection, we have stormy weather at D2, which is the intertropical convergence zone, where the air from the northern and southern hemispheres coming together and rising and giving us huge thunderstorms and cumulus clouds over the equator, and we see that pattern of clouds from space as a very persistent pattern. We also have stormy weather at the polar front, which is given by D3 and D1, and that's not due to intense convection, but it's due to the fact that we have warm air in the subtropics coming up along C2, we have cold air coming out from the pole along C1, so we have high temperature contrast at the boundary at the polar front, strong pressure gradient force, and therefore both a strong jet stream but also rising air coming up with the moisture coming from the subtropics, giving us stormy weather. Turning to G, the surface weather map of the United States, we see fronts A, B, C, D, and C upward. We have identified a pattern of high and low pressure systems, which are the A circles, and we've identified air masses, which are the B circles. And so the first question is, where do we have representation of where a warm air mass is moving forward and overrunning a colder air mass? And this, of course, is a warm front, which is CD. Warm fronts are indicated by, here we have warm air coming from the southeastern United States up to the mid-Atlantic, overrunning the colder air at the mid-Atlantic, and the little biscuits are pointing in the northeasterly direction, and that's the movement of the air mass. The curve is called a warm front. In this pattern, if I look at the pressure values, an anticyclone is a low pressure system. A low pressure system is usually at the center of intense precipitation, as evidenced by the green. The high pressure systems here are all inside local maximums, 1028 millibars, 1024 down over Florida. So the anticyclones are found at A1, A2, and A4. The cyclone is found at A3. You're only asked about the anticyclone here. Marine tropical air would be coming in from the Gulf of Mexico, and so marine tropical area is coming in on B4. The other air that's in the mix here is we could have marine polar air, cold marine air, and that would be evidenced by B3 and B1 coming in from the Atlantic and the Pacific. And we could have continental polar air coming down from Canada in B2. And so continental polar air is found at B2 in this problem. I don't know why B2 went missing in the printout, but B2 is continental polar air. Finally, putting an X where I think we might expect fog, I put the X at the warm front. The kind of weather I expect. Remember that at a warm front you have a very gradual overrunning of the warm air with the cold air. The distance along the ground under a warm front is much longer. At a cold front you have dense cold air pushing up against warm air. It's a very abrupt transition, and you get intense weather at the cold front with deep cumulus clouds and storms. At a warm front you get more gradual weather. It begins with fog along the front. And the cross inside a circle I have placed where the isobars are closest together. Remember, where the isobars are closest together is where we get the strongest pressure gradient force and therefore the strongest winds. And so we turn to the last part of H in the problem. In the general circulation there is a jet stream aloft at the polar front. This jet stream winds blow from west to east. Briefly explain why these jet streams aloft occur. In your explanation, describe the role of pressure gradient force and the Coriolis force in creating these westerly winds. And so at the polar front, as we saw earlier in the general circulation, we have cold air from the Arctic coming south towards the equator and meeting warm air that's come up through the subtropics. So at the polar front we have a very abrupt change in temperature. Therefore we have a warm column of air on one side of the front, a cold column of air on the other side of the front, with significant temperature difference, and therefore we get a strong pressure gradient force, as we saw as we discussed the fact that the warm air mass extends high, the cold air mass tends to shrink. At any altitude in the air masses, at the same altitude, there's a higher pressure on the warm column than there is in the cold column, and so we get a pressure gradient force from warm to cold. That strong pressure gradient force makes the winds blow northward across the polar front, but the Coriolis force pulls them to the right, and so they travel in a eastward direction. So it's a northeastward wind, which is a wind that comes out of the southwest, and so we get a southwesterly wind. The fact that we now have a jet stream that moves along the polar front and it bobs and weaves, we get convergence and divergence in its flow, and that's why we get the support for the cyclones at the surface below, and that's why we get the storms associated with the Aleutians and with the North Atlantic. We add to the mix that the subtropical air coming from the south carries a lot of moisture in it. It's warmer air, and so we have all the moisture we need for good storms and good precipitation. So all the ingredients come together at the polar front.